Dr. Scott, Professor Scott, thank you very much for talking to me today. We both are fully vaccinated, so I'm glad we can be in the same room, no masks on, being able to talk. So I wanted to talk to you about a number of things on thermal management, tools, modeling, heat pumps, teaching, autonomous vehicles, all of that. And so you've taught mechanical engineering at University of Virginia for 40 years.
40 years.
And you want to say more?
I taught some here at U of M when I was doing my PhD work. So I've taught in a number of places, and now I helped start the engineering program at Sweet Briar College, which is only one of two all-women's colleges with an accredited engineering program. And
nice.
We've been working on that for 14 years, and it's a pretty good success. Small college, but...
Yeah, that's awesome.
Yeah.
So maybe we can start there, because I am also developing a course for Wisconsin-Madison on thermal management, and I wanted to ask you, when you're developing courses or when you're teaching them, what are you looking to include in the courses that you go, aha, they don't teach that?
Right. Well, topic number one would be the fact that most everybody agrees now that there's no such thing as a single discipline engineering problem. And Sweet Briar's program, like a number of others, is an engineering science program, but it's rapidly turning into what the current buzzword is an integrated engineering program. There are a number of places who have officially called their programs integrated engineering. Northwestern has got one, and a few other places. And it's a general engineering program that tries to cover basics so that the graduates can be pretty comfortable wherever they go.
Mm-hmm.
So that's the first new trend that I think we're going to see more of. The second thing that we managed to do at Sweet Briar is there's some unique things there. One is all the students at Sweet Briar are required to take 2 years of a foreign language, even the engineering students.
Oh, that's interesting.
We also have a required summer project that the students do, and in many cases we've had an activity where we go to South America and build a canal system for a Guatemalan village or something like that. So if you graduate a student in engineering who's got a foreign language and a foreign project experience, this makes your graduate look really good to a potential employer.
Yeah.
Because it's an international world now, right?
There's no North American company. Yeah. It's a global industry.
It's a global world, and that's something that our graduates have. We also do projects with local industry, and the Lynchburg area where we're around has got a lot of high-tech industry.
Mm-hmm.
And we do projects, all of our senior design projects are connected in some way with some local company, be it large or small. And that helps us. Plus, an internship is required of all the students. And pretty much everybody who hires our students as an intern wants to hire them after they graduate.
Yeah.
We can't produce enough graduates. But you were suggesting before some of the things that we do that you won't find in other places. If you're practicing in the business, you learn a lot of things on the job which you don't realize.
Mm-hmm.
What does SCFM mean, for example? If you look in any fluid mechanics book, you won't find SCFM described anywhere. You also will probably not find HVAC or MSDS. And, of course, SCFM is standard cubic feet per minute. I make all my students memorize all those acronyms, LPM, SCFM, and I point out to them that part of being a success in engineering is knowing the right buzzwords.
Well, one of the things that I found that I include in my course is some first principle fundamentals about why did we pick the coolant that we picked? Like, why is it 50-50 and why isn't it? Could be a different mixture, would that work? Or what properties of that coolant matter to us a lot? Is it the heat capacity? Is it the freezing point, boiling point? But also, should we care about the viscosity of the coolant? How do we figure out what the coolant pressure will be in the system? Yeah. Like it's not, some of these things are not quite obvious until you really think about what's driving the pressures, what's driving the flows in the system, and being able to think about it from a fundamental first principles perspective.
And you've got to replace the derivation of the Navier-Stokes equations or something else with that.
Right.
And if you think back on your own college days, you essentially learned nothing. Yes, you memorize material to get through the course. Students today are even worse than we were because many of them don't buy the textbook. It's online, so they don't walk out with their degree and a pile of books to read, to use as references. And you thumb back through the chapter to find an example problem that matches the homework. We all did this. So what you stress in your course is the only thing they walk out with. One of the things that I do is I give them a list of outcomes for each lesson that says, these are the things you're going to have to memorize from this lesson, and they're going to be on a quiz. Students like to see that, but it also gives you a chance to put in the things that are important.
Mm-hmm.
And with fewer and fewer academics having any industrial experience, we're getting further away from the practical aspects of what we teach. Yeah. So we need to do more of that.
Your textbook example really strikes a chord with me because some concepts and formulas, I don't remember them off the top of my head, but I have a visual memory of where in the textbook it is. And so I can pull it out, I can flip to that page, and I can see exactly where it is.
Well, that shows you how old-fashioned you are. You're supposed to, like my grandson said, you're supposed to just Google it.
That's right. That's right. Yeah, and the internet is always right.
And the internet, yeah, well, the question of whether the internet is right or not doesn't seem to come up. Yeah. If you look at some of the where you were when you were in before we had calculators and you had to learn how to multiply and divide by hand.
We weren't allowed calculators in our school. We had logbooks.
We didn't have calculators when I went to school, and so we spent a lot of time manually calculating things. I can tell you an incident where the biology teacher at Sweet Briar had a student in his office and said, well, if we take 5 samples from these 8 bins, how many samples will we get? And the student reached for a calculator and started crying, literally crying, when he said, that's a number we could figure out ourselves. Now, if we've gotten to that point with respect to those basics, relying on some algorithm to do everything for us can be a scary prospect to look forward to.
Yeah.
Some of these problems I don't know how we fix.
Agreed.
But I keep trying until they take me out in a pine box.
So let's switch to automotive subjects.
Okay.
And one of the things that you and I have been talking about quite a bit recently is heat pumps. And for those of them watching who don't know much about heat pumps are essentially air conditioning systems run in reverse in order to pump heat into the cabin from the outside. Of course, there's more complexity to that than just running them backward because you can't exactly run them backward, but that's the concept, right? So talk to us about what you are thinking about heat pumps. So many cars didn't have them in the beginning. As an example, Tesla's first cars didn't have heat pumps. They said they couldn't justify the additional complexity and cost. But then the latest Tesla does have a heat pump. So where will we see heat pumps on all electric vehicles?
We will see heat pumps in every electric vehicle that's out there. And the trade-off with heat pumps is the amount of energy it takes to run it and how it affects the mileage, how far you can drive the vehicle.
Right.
As the cost of batteries goes down and battery efficiencies go up, you can afford to use more heat pumps as long as you can go a certain distance. But this is certainly a new field with a lot of new challenges.
Mm-hmm.
As we know, an air conditioner takes energy from a place where it's hot and
mm-hmm.
gets rid of it to some place where it's colder, and a heat pump just runs it backwards.
Mm-hmm.
So you have to take energy out of the cold air outside and increase it with a compressor and then reject it inside the cabin.
Right.
Residential heat pumps have been around for some time, but in certain states where it's very cold, like here in Michigan, for example, residential heat pumps are not as attractive as they are in the South.
Because they don't work in all
Because
zones.
The colder it is outside, the less efficient the heat pump becomes. And if you want to have a more efficient heat pump, you have to spend more money on the components, more efficient compressors, larger heat exchangers, and a cost-benefit analysis for a residential environment
mm-hmm.
in a climate like this, the trade-off is not to your advantage. So you're better off to go with gas-fired furnaces or electric emergency heat. This is the issue that the electric vehicle heat pump system runs up against. The cost and complexity of the system, the amount of space you have to put the heat exchangers in.
Mm-hmm. The heat exchangers are already in there. So you have the condenser and the evaporator already in there. So the complexity is coming from probably not additional heat exchangers, but the valving system to run it backward,
well,
right? And controls.
The current versions, such as the ones in vehicles that are out there now, in the hybrids and the electric vehicles, simply reverse the direction of the refrigerant flow.
Okay.
The two heat exchangers are designed originally to operate as air conditioners, and so the direction of refrigerant flow through them is set up to be best for air conditioners. Now you're going to run the refrigerant flow in the opposite direction, and if you want to get the best performance out of it as a heat pump, you need to rechange the piping so that the refrigerant goes in the bottom of the heat exchanger instead of the top. Mm-hmm. That's an added complexity, which at present people have decided they don't want to pay the price for.
Okay. Does it not pay for itself? Is the efficiency not improved enough to pay for the new plumbing?
At present, it's not enough to pay for itself.
Oh, okay.
And the additional valving and controls you have to do to make this happen, as opposed to just keeping the same pipe, just running the refrigerant in the opposite direction. All you have to do is change the piping around the compressor. But if you want to change the piping around the two heat exchangers, that's an additional complexity which adds to potentials for failure and additional manufacturing issues and getting the configuration in the vehicle. They're not yet ready to do that.
Right, because typically in an air conditioner you have the hot compressed gas coming into the top, and then as it cools off, it turns into liquid, and it naturally comes down to the bottom of the condenser. Now, when you run it backward, you have
liquid coming. This is the condenser that's out. This is the heat exchanger that's out in the front of your vehicle,
right?
Okay, which serves as the condenser in air conditioning operation, and vapor comes in the top, condenses, and comes out the bottom as liquid.
Yeah.
Now you're going to run this as an evaporator where you bring liquid in and it's going to boil. Well, boiling vapor wants to rise, so you're pushing it in the opposite direction. And the circuiting of when it's operating as a condenser, the circuiting is set up to optimize the vapor liquid space, how much volume you need for it. Now you're taking the same thing, running it backwards. It's not optimized for the job. So you probably lose on the order of 20% of the performance that you could have if you just made the liquid come in the bottom instead of coming in the top. Well, that trade-off has not been accepted yet. And it may turn out that battery prices and battery sizes and battery efficiencies may go up fast enough so that you don't have to deal with that issue.
Yeah.
There's some real interesting things to look at in the future.
Yeah.
Now, let's not forget the electric compressor.
Right.
Okay, the mechanical compressors were running 5 to 6 horsepower.
Right.
10 kilowatts.
Mm-hmm.
With an electric vehicle,
you have that.
You don't have that kind of capacity. The 48-volt AC compressors don't have the volume. They can't process as much refrigerant.
Mm-hmm.
If you're going to go to a 400-volt system, you can get a compressor that'll put out 4 or 5 kilowatts, require 4 or 5 kilowatts. Do you really want to do this? There are a multitude of decisions that have to be made here.
Right.
And the costs and regulations are going to tell us which way we go. But I think we can be pretty confident that every electric and hybrid vehicle is going to have a heat pump of some kind in it.
Yeah. And but it doesn't really affect the published range, because you do the 5 cycle and one of the cycles is at -7. So it could be -7. And heat pumps don't really play in that space.
They could. Remember that if you have to put more energy into the compressor than you can get out as heat on the other end,
mm-hmm.
then you might as well just take the electricity and have a resistance heater inside the vehicle.
Right.
You improve your compressor efficiency, you can run at lower temperatures
mm-hmm.
and still balance that. If you make the heat exchangers big enough, you can go down to below 0 temperatures and still run that. But the whole front end of your vehicle has to be a heat exchanger.
Yeah, I don't know if anybody wants to touch that.
Nobody is doing that yet,
mm-hmm.
but certainly we can improve the compressors. We can improve the compressor efficiency.
Yeah.
It remains to be seen.
Yeah. What are your thoughts on the octovalve that Tesla had? Just an engineering combination of reversing the flows and
a number of these multi-component valves have been proposed for transmission oil coolers heaters that can move 2 sets of valves. Some of them have wax thermostats on one end or the other.
Right.
There have been a lot of leakage and issues with these failure mode problems.
Right.
That may or may not have been overcome yet.
Mm-hmm.
Eventually, this will get fixed.
Yeah. So, refrigerants. How does what are your thoughts on refrigerants? Because North America is headed towards YF as a replacement.
Yeah.
I don't think Europe has decided yet, and neither has China, if I'm not mistaken. Yeah,
that's right. And the decision so far, just about every refrigerant change we've made has resulted in a reduction in performance of the system. It's not. We've gotten to the point now where probably it's going to be a few percent changes if we change refrigerants.
Okay. Most of the ones that are being considered in Europe and China have a similar performance to YF?
Yeah.
Okay.
It's not going to be that much of a detriment to do that. Yeah. We already went from R12 to 134A and 1234YF. We lost quite a few percentage in those original changes. I don't think that the penalties are going to be that much greater. The big cost is changing everything around,
mm-hmm.
because you have to sometimes the seals and one of the problems with R12 was the rubber seals in your compressors couldn't take it with 134A, so you just had to change everything. You may have experienced this in your house when you had to switch over to a different refrigerant from R22. You had to replace every component in the system.
Yes. In fact, we had to have a completely new system put in there because they said that they couldn't repair the old stuff. So
the customer is going to end up paying the price for this.
I just did, actually, last month.
That's right. Yeah.
Okay. So, controls. Heat pumps.
Yeah, heat pump controls. When you're trying to use the least amount of electricity possible to run this, the freezing up on the outside heat exchanger when you're in heat pump mode becomes really critical. If you have to defrost every time you defrost, you're using extra energy. You're not getting the heat in the cabin that you want, and the cycles of defrost and frosting up again, and how you detect when it's time to defrost. We haven't solved that problem yet, and the control systems that we have now are pretty crude. There have been a number of proposals, a number of which that don't make sense. Some people have said, well, let's put some of these coatings on the fins of the heat exchangers so that they don't frost up as much, or when you defrost, the water runs off better.
Do they work?
Until you run through a mud puddle.
Okay.
And you get the fins all covered with dirt, then this coating is
not effective.
And someone else has pointed out that if you're driving down the road and your heat pump is heat pumping and it's not frosting up, but it starts to snow, or you start splashing through salt puddles and splash water up in the front end of your vehicle, in the past, you had a nice hot radiator in the front.
Right.
Snow came in the front, you didn't worry about snow buildup. Now, you've got a heat exchanger, the surface of which is colder than the air passing over it.
Right.
And how do you set up a frost-defrost control scheme that accounts for the fact that, gosh, we didn't expect water to splash all over the front of this from that puddle we ran through?
Yeah. So where do we stand today? So of the 30 minutes of heat pump running, how many minutes do you think it's actually cycling to?
Sometimes it's running, depending on the humidity of the outside air, sometimes it's running 10 minutes and defrosting 3-4 minutes. And as I pointed out once before to you, at the end of the defrost cycle, you've got water on the heat exchanger fins.
Right.
And if you don't get all of it off, the minute you turn the heat pump back on, you've got blocks of ice between the fins.
Right.
So do you run your fan backwards to blow the air out? There are some people that have proposed that if you've got a hybrid vehicle and you've got an engine that's warm, or you've got a radiator that's warm, just running your cooling fan backwards will blow hot air over the condenser in the front, which is now an evaporator, and help defrost it and blow the water off. There's all kinds of combinations, and my assessment is we haven't sorted all this out yet.
Yeah.
The frosting problem, which I've been looking at recently, the only models for frosting growth have been written for nice constant velocity, constant humidity air flowing over a nice flat plate at a constant temperature. There are no good models out there that can predict frost characteristics or how fast the frost builds up over time.
Right.
Anybody who says they've got one is fooling you, and that's not a problem that I think we can fix, which means a feed-forward control system for defrosting, where you can predict in advance when the frost layer is going to get thick enough that you need to defrost. I don't see being available at all. It's going to have to be, you have to watch some parameter that tells you when you're going to have trouble. And I've been looking at signature analysis. Are you familiar with the way this works?
Oh, please do tell.
Signature analysis happened originally some time ago with large turbo machines, particularly in the electric power generating. You've got a giant steam turbine generating megawatts of power, and if one of its bearings fails, you're in big trouble. So when you install the steam turbine, you put an accelerometer on the bearing housings, and you record a signature analysis of what the vibrations look like. And you watch that over time, and when you start seeing deviations from the baseline signal, it's telling you that your bearing is starting to fail. And so you get in and fix it while you got this in advance. I tend to think that that that's the only intelligent way, or one of the only intelligent ways we're going to be able to deal with this heat pump system. You either watch, for example, if you put an accelerometer on your heat exchanger, and when it gets frosted up, its mass increases because of the frost, and you have natural vibrations of heat exchangers, which you have to satisfy to sell the heat exchanger to a company. The auto industry wants you to do vibration tests. There may be some way to note that the mass increased and the stiffness didn't, and you can see a signal that tells you the mass of this heat exchanger is increased. We're probably building up frost.
Right.
Those are some of the ideas we have to start looking at in the controls side of this.
Are you thinking an external sensor on top of the condenser that's detecting frost, or are you thinking you would be able to detect it based on the fluid properties inside?
Well, you can't detect the frost by itself because there's no way you can measure it.
Right.
There's an increased pressure drop across the heat exchanger when it's frosted up, but measuring the air side pressure drop across an outside heat exchanger the sensors are not going to be that reliable.
Plus it depends on a lot of
things.
It
depends on fan speed and everything else.
And temperatures.
We've thought about looking at the current draw by the electric fan, but it turns out that in the low flow rate, high pressure drop range of operation of the fan, which is where you'll be when the system is frosting up, the current to the modern electric fan motors doesn't change that much.
Is it also possible the fan's also not on? Like there are some scenarios, it's cold outside and there's enough...
but in that case, the freewheel RPM of the fan can tell you how much airflow is going to give you an indicator of this. But this is a problem we haven't solved yet. These are all things that we need to start looking at.
Right. Agreed. Tons of
fun for us.
Stepping away from heat pumps, but looking at the same things for general thermal management. Like, what still needs to be solved in thermal management?
Vehicle thermal management.
Yeah, just overall.
Vehicle thermal management. There's the powertrain itself, whether it's a internal combustion engine or battery-powered systems. In the internal combustion engine powertrain with turbocharged engines and charged air coolers, the amount of heat rejected by the internal combustion engine is now considerable.
Right.
And trying to package the heat rejection heat exchangers in the front of the vehicle is almost impossible. If we're going to do that, we need to rethink the entire aerodynamics of the front of the vehicle. Look at ducted radiators. The new Corvette that's got the rear mid-engine that's got its radiators back in the back is the kind of thinking we have to start doing for other vehicles. And
that's straight coming from race cars, isn't it? Where the ducted radiators, like the heat exchangers,
ducted radiators were used in the aircraft, World War II aircraft, for the Spitfires and the Messerschmitt 109s had ducted radiators to get the best performance and to reduce the pressure drop. So our whole front end of vehicles is not configured for that. It hasn't been because we've had plenty of space. Now we need to relook at that. When you go to and there's also the thermal management of recovering. What's the best way to recover energy from the hot coolant and the hot exhaust? We still haven't satisfied ourselves, so we've got a good handle on that. Mm-hmm. The control schemes for do you heat the transmission oil first or the coolant first or the engine first? A lot of people are looking at that, and there's some good ideas out there, but it's a challenging issue. When you get to hybrids and battery-powered vehicles, we're in the process of trying to figure out what's the best way to thermal manage battery packs.
Right.
As power density gets tighter and higher, people are still working on some innovative schemes for cooling these battery packs. Immersion cooling is out there now, but it's an area that we don't have a lot of experience in.
Yeah. What I'm liking that I see is that when heating or cooling is required, you can look around the system and say, like, what else is producing heat besides me having to spend electrical energy on it? So you have the motors that are generating heat, you have the battery that's generating heat, And so if you say, well, I need some heat in the cabin, perhaps some of these components you'd be able to pull heat out. And on a flip side, if you look at the cabin and you say, I need energy to heat the cabin, the work that's being done is more around, well, so what exactly are we trying to heat? Oh, we're trying to keep the driver comfortable. Yeah. Oh, so we don't really need to heat the whole cabin. It's the driver. So, okay, where? Like, what do we need to do to make the driver warm? Is it the arms? Is it, the back, the neck? And where exactly do we need to focus the energy, either heating or cooling?
Yeah.
Without having to do the whole thing.
And there are lots of good transient human thermal models out there now that you can get that do a really good job. And people are now starting to look at concentrating the heating and cooling on the human instead of the cabin itself. Mm-hmm. There's a lot to be learned from the aircraft industry, which has looked at efficient cooling of passengers in aircraft by these little air jets above your head. Mm-hmm. There has been a lot of work done in the aircraft industry on that. The automotive industry needs to start looking at that. There are a number of people who are now looking at directed air jets and heated and cooled seats and how that affects the thermal comfort of the passengers. And a number of automotive people are also now looking at maybe it's time to start insulating the cabin, mm-hmm. putting insulation in the headliners and the doors. These are things which we didn't even think about looking at 20, 30, 40 years ago. Mm-hmm. But now it's becoming critical. It's surprising that we haven't looked at this in the past.
I'm surprised that there isn't insulation. I thought that there was insulation in the doors.
Yeah, but no. Well, in many cases, for years you had so much throughput of air. Your exhaust air out of your exhausters was high enough mm-hmm. That the loss, that was one of your major losses. 40, right. 50 years ago, you were losing a lot of heat just because you had body leakage that was bad.
Right.
Then you tightened up the body so you had not much body leakage, and then you had windshield fogging and other problems because you couldn't get rid of enough air for the humidity. So now we've tried to reduce the air that we push through the cabin mm-hmm. by doing more recirculation of air instead of bringing in fresh outside air. Then you have to look at air quality. And for the first time, we're starting to look at all of those factors combined. This is good.
Yeah, indeed. I mean, because now it's thermal management is really like energy management. There's thermal energy isn't coming free from the engine. Yeah. It's coming from electrical energy, which could be used for many things, including driving computers, sensors, and all that stuff.
Lots of fun for us.
Autonomous vehicles.
Yes.
What do you think of it?
You need to read it. There's a book out called A Brief History of Artificial Intelligence. I just finished reading it. Okay. It's the book I was reading, showing people when my grandson told me. It's an excellent book. It's written by a guy who's got 50 years in artificial intelligence. Okay. And
do you know who the author is?
I can't remember the author, but it's just a brief history of artificial intelligence. Just came out last year, and he spends a good deal of time talking about autonomous vehicles and also about artificial intelligence in general, the things artificial intelligence can do and the things that it can't do. And he spends a lot of time on autonomous vehicles, and autonomous vehicles can only do what they've had experience at. In order for an artificial intelligence system to work right, it has to have witnessed everything. An artificial intelligent person to replace you would have to have witnessed everything that you have witnessed in your life.
It needs a lot of data.
It needs a lot of data, and the nuances of driving down the road and having a deer jump out in front of the car, the things that the artificial intelligence system has to consider before it makes the decision as to what to do exceed the amount of knowledge that it can have. It can't recognize every animal that comes across it. Mm-hmm. So autonomous vehicles are probably going to be relegated to situations where the environment is structured well enough that...
I would also, I would 100% agree with that. The structured environment is a secret to it, because unstructured has too many unknown things, called the long tail. Too many things it has not seen. Yeah. But something that is structured and has rules. So I can imagine, a computer would beat a human in chess because it's fixed, structured. Yeah. But when it comes to a conversation, which can go anywhere and there's really no structure to it, then it would struggle with things that it has not seen before.
And the book has, the guy who wrote this book has a very wonderful way of making this clear to you, and I shall use an example from his book. You are to evaluate a conversation where Mary is talking to Judy, and Judy says, Bob's husband is not going to be home for the next week. He's going off to Europe on business. And the other woman says, well, who's the woman? Now, just from that snippet of conversation, you're able to figure out that it's apparently that this guy is probably not faithful to his wife, and so this other woman immediately thinks that. Right. But in order to come to that understanding of the conversation, the amount of information you have to have in order to deduce that, to make sense of it, is huge. Right. Just taking those two phrases and giving them to somebody artificial intelligent, what does this conversation mean, illustrates why artificial intelligence is really a lot more limited than we think. Yeah. I would say that it's too easy to diss AI or autonomous vehicles, but I think we ought to really think about what the killer app for the autonomous vehicles is, because it's coming, and perhaps it'll take longer than people claim for it to come, but I would say that it's coming. And saying it would never happen, I would say would be maybe standing on the wrong side of history. But for it to be successful, it has to make business sense or market sense first. And for that to happen, I think it needs some kind of a killer app, whether it be being able to transport, people who can't drive, or be able to run services 24/7 at a very high frequency, where typically it's not done because you can't pay people to do that. Or I don't know what it is, but I think it needs some kind of a killer app that people say, aha, this makes business sense, and this is where it really works. We will pay for it. And this author seems to think that it's about 5 years out.
Oh, that's pretty aggressive.
Yeah. And of course, dealing with the legal issues of if one person gets killed by an autonomous vehicle, well, 30,000 people get killed by humans driving around. At some point, you've got to have a trade-off here. So there are some legal and business issues to deal with. But the technology, satisfactory level of technology for enough of these to come out, he thinks is 5 years off.
Wow.
So get yourself a copy of the book.
Oh, absolutely. Did he say what application that it would be, or is it general public driving?
No, general driving. I'm sure it's going to be in structured environments, but right. Now, I'm getting old, okay? And I would sure like to have an artificial intelligence system to help me figure out how to use my cell phone. Right now, I use my grandkids. Mm-hmm. But there's no reason why autonomous systems cannot take on a lot of these things, which are pretty much straightforward. An autonomous vehicle, I could buy a new iPhone and say, please connect this to my car, please put my calendar on it, please do this, please do that, which I don't know how to do. Right. And so there are plenty of places where artificial intelligence has gotten to the point where it can be really helpful. And if you get a structured enough environment, such as my cell phone or my computer, I dread buying a new laptop because I have to reset everything up. Just do it for me.
Yeah. Alexa's getting there, but it's not quite there yet, because when I ask it to play a song, it doesn't play the kind of song. The version of the song that I want it to, it plays.
It needs to know you better.
Exactly. I actually tell it exactly who I want it by, and it still doesn't get it. Anyway, but it's getting there.
Allow me to give you some history. When engineering first started out, it was civil engineering for military stuff, how to design cannons, how to build bridges quick to get across the river before Napoleon catches up with you. In the 1880s, mechanical engineering really started in the end of the 19th century when we had figured out all the equations. But the number of applications of engineering was limited. The only fluids we were pumping around were sewers. In 1880, you didn't have city water coming to your house or a city natural gas line, but you had to get rid of the sewage, which was why all the fluid mechanics stuff was done by Darcy and the French sewer systems and everything. If you went to an engineering school and had an engineering program, say in 1920, what you learned in the thermal sciences was what you needed in order to run a steam power plant. If you needed to calculate the pressure drop in a pipe, the only pipe you had to calculate the pressure drop for was one carrying water or sewage. You didn't have to pipe refrigerant or anything else. And so in engineering school, you were given a set of canned formulas. If you design a pipe for water, you use the Hazen-Williams formula. You plug these numbers in. And what we did was, the educators were also smarter. They realized that we're basically stupid and we're just going to memorize stuff to get through the course. So they made darn sure that you practiced using these canned formulas long enough that you just knew how to use them and didn't make a mistake. There weren't any computers. Then in the 1960s, when Sputnik went up, and I was there, when all the education changed and everybody thought that we needed to teach students how to derive all these partial differential equations, and the net result was nobody could calculate anything because you didn't practice over and over again. And none of us understood the derivations of the equations anyway. Students are just as dumb as they've always been. But today, in place of the canned formulas you memorized and calculated over and over in 1920, you now have a software package that you learn your stuff from and you just blindly use. So we're just as dumb as we were in 1920. But because there are more problems we have to solve, we have computers that do it for us. In 1920, we didn't question the formulas in the book because they'd been developed over years of practice. Today, we don't question what the computer tells us to do either, except there are very few practicing engineers trying to keep these formulas the best they can be in the software package that deal with thermal and fluid stuff, as I've pointed out. They were thrown together in the last 20 years, and they're not as good as they should be. So the good news is people today aren't dumber than they were in 1920. The situation has changed.
People are people.
People are people, and I'm hoping that over the next 10 or 20 years, the software packages for thermal fluid stuff will get good enough so that we can actually rely on them. Because we had to rely on the formulas in 1920. We just assumed that they were right, and we designed boilers and they worked. We're not quite there with the thermal fluid stuff yet. And we're not going to get there by me screaming and yelling about how the formulas are not right. We're going to get there when CFD becomes so fast that you got to analyze flow in a pipe, just run a CFD model up. Even though you can calculate.
I find that a sledgehammer approach. I cringe when...
But I'm afraid that's probably where we're going to get. Sorry. And it's the fault of humans. We basically just take the easy way out.
Sorry. You mean the brute force way out?
No, I don't have to think. I just click on this icon and drag it onto the screen, and
Don't you think CFD has the same limitation in the sense that it calculates what whoever set it up tells it to calculate? So whatever simplification or unknown mistaken assumptions one would make into simplified formulas will be made in 3D CFD as well, in fluid properties or boundary conditions.
Yeah, the big problem with CFD is we still don't have good turbulence models. We've got 6 or 7 different ones you can use. Yeah. Some of them are better for some situations than for others. That may or may not be fixable. But as opposed to letting people figure it out for themselves, we're going to have to live with it.
Right.
But just like when you use your calculator to multiply 2 numbers together, the idea that the result it gives you might not be right is not something that worries you. People using these software packages don't even think about the fact that the number might not be right.
Right. That is one of my pet peeves as well. Not necessarily not knowing what analysis you're doing. A lot of times you would have these fresh graduates that would come, use software, drag, drop, punch in numbers, hit calculate, and go, oh yeah, 52 GPM, for example. And they would say, okay, that is the answer. Right. Without really thinking through, well, does this make sense? Is it in the ballpark where it needs to be? And to my team, I stress that you ought to be able to do a rough ballpark calculation with pencil and paper first to know where the answer would lie and what the guiding forces are before they actually build the model. Because if you don't know what the guiding forces are, sort of the free body diagram, what is pushing and pulling properties, fluids, etc.
If you've got the time and the patience to do it,
it's a step you can't skip.
Well, lots of people are skipping it. If you're not, this is good.
Well, otherwise you can't be confident in the numbers.
Yeah.
All right.
It's always a pleasure, my son.
Our pleasure. Thank you.